Alright, today's video lesson is on solubility product calculations. So I'm going to run through a number of the types of solubility product calculations you're going to go through. Okay, so this is a typical problem you're going to see. By the way, this should actually be all referring back to chapter 16, so I apologize for that, but these are all from chapter 16. Anyway, calculate the solubility of each of the following in moles per liter. Okay, so Ksp is not solubility, it's the solubility product. So what we're going to do is we're going to start with A, and what we're going to do is we're going to look at the dissociation reaction, which is the breaking down of the solid into its ions. So what we end up with is nickel 2 plus, and we end up with carbonate 2 minus ions in solution. Alright, we're going to use the ICE table here, ICE for this. And we don't care about the solid phase, that's not important. What we're concerned about is the concentration of ions. Now, what we're going to do is take that concentration of ions and backtrack to the concentration of the nickel carbonate. In this case, what they're looking for is the solubility of nickel 2 carbonate in water, not necessarily the ions, but they're all connected. I mean, if I dissolve this into water, I get those ions into solution. Alright, so it's real simple. This starts off as 0 in the ICE table. Alright, and then we set that equal to 1.4 times 10 to the minus 7. And presto, we can do is solve for x. And x comes out to be 3.74 times 10 to the minus 7. Nope, to the minus 4. My fault. I saw the 7 up there. So to the minus 4. Okay, and that would be molar. Moles per liter is what we're looking for here. All right. Now that's what X is, and that's the concentration of the nickel ions. But where did those nickel ions come from? They came from the dissolving of the solid. So if I think about this and I just do some stoichiometry, 1 mole to 1 mole is going to be the same. So therefore, that would be the solubility of my nickel 2 carbonate solid. Okay, so pretty much the same idea there. And as I said before, X is almost always going to be your solubility. So your solubility is almost always going to be that value X. Okay? All right, let's take a look at the second part there. Right, so B. Again, I'm going to start with the dissociation reaction, or the equation, which is breaking this up into its particles. So it's the solid. And I dissociate this into ions, and I'm going to get 3 barium 2 plus ions, and I'm going to get 2 phosphate ions in solution. Okay, so I end up with 3x and 2x. Okay, so come back down here to my Ksp expression, plug in for barium 2 plus. I'm going to take that and cube it. I'm going to multiply that by my phosphate, which is going to be squared. So I'm being careful to include those coefficients in my expression. Then I'm going to plug in my 3x cubed and my 2x squared. Okay? Now to simplify this, a lot of students get this a little confused. A lot of people want to make that a 9. That really should be 27x cubed, and we're also going to multiply that by 4x squared. Okay? Now when we simplify that even further, we're going to end up with Ksp is equal to 108x to the 5th. Okay, so be very careful. Again, if it's a 3 to 2 ratio, it's always going to be this. 3 to 2 ratios are always 108x to the 5th, every time. Okay, so this is going to be set equal to its Ksp, which is 6.0 times 10 to the minus 39. And I can solve for x. And x is equal to 8.89. Two significant figures technically, so let's just make that 8.9 times 10 to the minus 9. And that would be my molarity. Now, be careful with this. This is the solubility of barium phosphate. That's what this is, the barium phosphate solubility, not the concentration of the ions. If I want the concentration of this barium, I have to multiply x by 3. If I want the concentration of the phosphate, I'm going to have to multiply it by 2. So be careful, because what you solve for here is x, which is the solubility. Okay? All right, so let's take a look at a different type of problem. do this problem, I'm going to keep in mind that I have strontium in here already. There are strontium ions in solution. So I'm going to put that 0.100 molar here. This is 0. There's no fluoride ions in solution. Next, I'm going to have the reaction shift to the right because I have no fluoride ions. So this is going to be plus x. I was looking at the fluoride. Plus x plus 2x. Okay? And 0.100 molar plus x, and we end up with 2x here. Now, this is what's referred to as a common ion effect problem. A common ion is an ion that's in the solution as well as in the solid that we are trying to dissolve. And this has an effect, and I'll show you what that effect is in just a second. But let's go ahead and solve for this. So I'm going to use Ksp, and that's going to be my concentration of the strontium, and again the concentration of the fluoride ion. And I'm going to have to square that. Plug this in here. Now, what are we going to be able to do with that x? Hopefully you all know that I can drop this x out because my Ksp is such a small number. The reaction is going to shift to the right, but it's not going to shift enough to make an effect on this strontium. So when I plug into my equation now, I'm going to plug in 0.100 molar times 2x squared. Okay, so now my Ksp is equal to 0.100 molar times 4x squared. And now I can solve for x. Okay, the solubility comes out to 4.4 times 10 to the minus 5 molar. Okay, now let's take a look up here. Up here I had 5.8 to the negative 4. This is now 4.4 to the negative 5. So what has happened to our solubility by having this strontium ion in here? Our solubility went down. Solubility decreased due to what's called the common ion effect. This is standard. Anytime you have a common ion in the problem, it is going to always reduce your solubility. So remember we said that Ksp doesn't change. This number is set in stone as long as the temperature is constant. Solubility can change, and I can manipulate solubility based on what other things are in the water. So if I put other things in here, I can change the solubility all I want. So every time I have a common ion, it's going to have an effect on the solubility. It's going to diminish it every time. And this is going to be really important in the next chapter when we get into acids and bases. Okay, I'll throw up the answer to C. I'm not going to show you live. I'll just kind of put it up here just to save some time, and you can see the last concentration.